Right now, the Pacific Ocean is heating up faster than it did before two of the most destructive hurricane seasons ever recorded, and it's about to flip a rule scientists have trusted for 50 years. Two oceans, one equator apart, and right now, they are living through completely opposite years. On one side, the Atlantic has gone unusually silent. Storms are trying to form and falling apart before they even get organized. On the other side, just a short stretch of land away, the Eastern Pacific is doing the exact opposite, spinning up storms faster than the calendar says it should, weeks ahead of its usual pace. Nothing physically divides these two oceans except a shift in water temperature that most people have never heard of. A shift strong enough to quiet one coastline while loading danger onto another. And forecasters agree on one thing: whatever is happening out there is not finished yet. When the 2026 Atlantic hurricane season opened on June 1st, meteorologists were already bracing for something unusual, a quiet year. Government forecasters predicted a below-average season, somewhere in the range of 8 to 14 named storms, with only a handful expected to grow into real hurricanes. A normal season, based on 3 decades of historical averages, typically produces around 14 named storms and 7 hurricanes. This year was being written down as underwhelming before a single cloud had organized over open water. By midsummer, independent forecasting teams had trimmed their numbers even further, putting this year on pace to be one of the quietest Atlantic seasons in over a decade. Fewer storms than any year in more than 10 years. Multiple respected forecasting groups, working independently, were pointing at the same ocean and arriving at the same conclusion: expect less from it than almost any year in a generation. Quiet is a dangerous word to trust, because even in a season built to underperform, the ocean has a loophole it keeps exploiting. Storms don't need the open Atlantic to grow. They can spin up fast and close to shore, in the warm shallow water of the Gulf, and make landfall before anyone has time to prepare. History has already proven this once. A storm during one of the quietest seasons on record still devastated South Florida. A below-average season is a statement about totals, not about the one storm that finds your coastline. So while the Atlantic was being told to expect a forgiving year, something very different was already taking shape thousands of kilometers away, in the exact same stretch of ocean that was supposedly behind all this calm. Most people who've heard the term El Niño picture it as a kind of storm, something with a strange name that arrives and leaves the way a hurricane does. That picture is wrong, and the truth is stranger. El Niño isn't a storm. It's a shift in the way the entire ocean moves. Normally, steady easterly winds push warm surface water across the equatorial Pacific from South America toward Asia, like a conveyor belt. That warm water piles up near Indonesia, while cooler water rises up behind it to fill the gap. During El Niño, those winds weaken, sometimes almost stop entirely. The warm water that should have been pushed west instead sloshes back east and piles up in the central and eastern Pacific, sitting there like bathwater that never drained. That pool of misplaced warm water is the entire event. Everything else, the floods, the droughts, the reshuffled storm seasons on the other side of the planet, is just weather reacting to one enormous puddle sitting in the wrong place. That puddle doesn't just sit quietly. It changes the air directly above it, and that changed air reaches across an entire hemisphere to reshape weather over the Atlantic. Scientists call this a teleconnection, a physical bridge built from shifting air pressure and rerouted jet streams that lets one ocean control the fate of another one, thousands of kilometers away. One of the clearest effects is something called wind shear, a mismatch between wind speeds at different altitudes. Picture stacking a tower of blocks while someone keeps shoving the top one sideways. A hurricane needs to build straight upward through the atmosphere, gathering heat into a tight spinning column reaching more than 10 kilometers high. Wind shear keeps knocking that column off balance until it leans, weakens, and collapses before it can ever fully organize. El Niño increases exactly this kind of shear over the Atlantic and Caribbean, which is the entire reason storms there keep struggling to survive this year. But that same warm Pacific water does the opposite thing directly above itself, feeding heat and moisture straight upward instead of shredding it apart. Warmer water evaporates faster, and warmer air holds significantly more moisture. When that moist air rises and condenses, it releases the energy that powers everything a hurricane does. One puddle, feeding one ocean while starving another. Most years, this warm patch shows up, nudges global weather slightly, and fades back to normal without much notice. Scientists track its strength using a stretch of equatorial ocean roughly between 5 degrees north and south of the equator. When that water runs more than 2 degrees warmer than average for several consecutive months, forecasters start using a different term, a super El Niño. That threshold has only been crossed a handful of times in the modern record, in the mid-1980s, the late 1990s, and again in the mid-2010s. Each of those events reshaped weather across entire continents, not just nudged it. This year, official monitoring agencies upgraded their alert level from a watch to a full advisory, confirmation that the ocean had crossed from possibility into an event already unfolding, with forecasters expecting it to keep strengthening through the winter. Then came the part that actually startled researchers. Multiple independent forecasting agencies on different continents, running completely separate models, converged on the same unsettling conclusion. This event was intensifying faster at this point in its development than either of the last two Super El Niño events. When independently built models agree like that, it filters out noise. The signal is far more likely to be real. The odds now sit above 60% that this becomes a genuine, historically ranked Super El Niño by the time winter peaks. In the late 1990s, during a strong El Niño year, a hurricane in the eastern Pacific strengthened into the most powerful storm ever recorded in that basin up to that point, winds strong enough to fling a car through the air. That record stood until another strong El Niño year nearly 2 decades later, when a new storm broke it again, becoming the most intense tropical cyclone ever measured in the Western Hemisphere. That pattern isn't a coincidence. It's the same warm pool doing the same thing, at the same phase of the same cycle, again and again. For 2026, the Eastern Pacific outlook calls for a season at or above average across every single category: storms, hurricanes, and major hurricanes. In the exact same season, the Atlantic was told to expect its quietest year in over a decade. And this isn't just a forecast on paper. By midsummer, the Eastern Pacific had already produced multiple named storms, running well ahead of its typical pace, arriving earlier and more often than the calendar says it should. So while the Atlantic waits, watching its few homegrown systems struggle against brutal wind shear, the ocean just on the other side is already busy, already ahead of schedule, already behaving exactly the way a strong El Niño year is supposed to behave. Which raises an uncomfortable question. If this relationship between a warm Pacific and a quiet Atlantic is really this reliable, why did it completely fail to hold up just a few years ago? Rules built from decades of averages have a habit of failing exactly when people start trusting them the most. In 2023, a developing El Niño was doing everything the textbook says it should. The Atlantic was supposed to fall quiet. Instead, it produced 20 named storms, a season well above average, because the Atlantic itself was running at record-breaking temperatures. Two forces pulled in opposite directions at once: El Niño trying to suppress the season, and record ocean heat trying to power it. The heat won. Even among Super El Niño years themselves, the pattern wobbles. Two of the strongest events on record reached nearly identical peak ocean temperatures, and yet produced completely different outcomes on land. One buried California under severe flooding. The other, despite matching ocean readings, left California drier than expected. The difference came down to exactly where inside the Pacific the warm water piled up, a distinction researchers now split into eastern and central flavors of El Niño, each with its own knock-on effects. Same thermometer reading, two different outcomes, an ocean apart. Layered on top of all this are slower-moving climate signals that can either amplify or blunt the whole response: decades-long ocean temperature cycles, tropical rainfall pulses that circle the globe every few weeks, even plumes of dry dust blowing off West Africa that can smother a storm before it ever gets started. Even the agencies tracking all this are careful never to promise more than the data supports. El Niño changes the odds of an outcome. It doesn't write the outcome itself, the same way loading a pair of dice shifts what number is likely to come up, without ever fixing the roll in advance. So the honest picture of 2026 isn't a season with its ending already decided. It's a season with its odds shifted, sitting on top of an ocean that has broken its own rules before. Here's the part almost nobody is talking about yet. What happens to an ocean this hot once all that heat finally has to go somewhere? Oceans this far out of balance rarely fade back to normal quietly. They tend to overcorrect. The same way a stretched rubber band doesn't ease back to its resting length, it snaps. Climate scientists have a name for this mechanism, the recharge-discharge oscillator. During El Niño, the ocean discharges heat upward into the atmosphere. Once that reservoir drains, the system tends to swing straight past neutral into the opposite extreme entirely, a cold mirror image called La Nina. And history shows this specific kind of event has a habit of ending exactly that way. Every clearly documented Super El Niño since the 1970s has been followed, within 12 to 18 months, by a hard swing into La Nina, not a slow drift back to normal, but a fast reversal, as if the ocean had built up more heat than it could hold and needed to dump it out as quickly as it came in. One of the more recent La Nina events lasted nearly 3 years, a rare, triple dip that's only happened a handful of times in the modern record. If 2026 follows that same pattern, 2027 wouldn't simply be a return to normal. It would be a flip. Everything driving this year's quiet Atlantic, the wind sheer tearing storms apart before they can organize, would reverse. La Nina tends to relax that same wind shear instead of strengthening it. That means the ocean that spent all of 2026 struggling to produce a single hurricane could spend 2027 doing the exact opposite. The last time a strong La Nina coincided with a warm Atlantic, the season produced so many storms that forecasters ran out of the alphabet. None of this is settled. A minority of researchers have raised the possibility that deep ocean warming, which now absorbs the overwhelming majority of the planet's trapped excess heat, could subtly alter how this whole oscillation behaves, potentially stretching out El Niño events or blunting the La Nina that follows. That remains an open question, not a confirmed one. What's actually certain is smaller than it sounds. The Pacific is running historically hot. Every Super El Niño on record has flipped into La Nina within a year and a half. Whether this one follows that same script, or whether something in the deeper ocean has quietly changed enough to slow it down, is the exact thing forecasters are watching right now. The ocean doesn't know the calendar exists. It doesn't care that a hurricane season has an official start date and an official end date. To the water itself, this isn't a chapter with a beginning and an end, it's one frame in something far longer, a rhythm the Pacific has been swinging through for thousands of years, long before anyone was alive to track it, and long after this year's storm names are retired and forgotten. What makes 2026 strange was never really about how many storms formed or failed to form. It was about watching, in real time, the exact moment one ocean went quiet because another one got dangerously loud, and realizing that the very same imbalance keeping the Atlantic calm might be the thing that eventually breaks it. Somewhere out past the horizon, the water that spent this year piling up warm in the wrong place is already moving toward whatever it does next. Nobody knows yet which direction that turn will take. Not the models. Not the agencies. Not the scientists who've spent entire careers trying to read this ocean. All anyone can do is watch a fault line that has already started to move, and wait to see which way it breaks.